Hi, and welcome back to Introduction to Deep Learning. Today, in tutorial number 9, we're going to look at facial key point detection. But first, I'm going to show a case study of exercise 8 and also have a recap of fully connected and convolutional layers. Then we're going to introduce exercise number 9, which is about facial key point detection. So for exercise 8, there again has been a huge number of submissions. So congrats everyone who tried to submit. And here we can see the leaderboard. And indeed, there are actually quite a number of students who reached very high number of accuracies. There are even 2 submissions with 100%. The first one achieved this through a CNN, which was implemented not as the torch layers, but basically re-implemented them individually. And the second one was actually using an MLP, how it was intended. So let's have a look at the MLP implementation. So here we can see the encoder architecture. So to recap, we had an encoder and a decoder, and then after the pre-training of the autoencoder, we also have a classifier. So here we have the encoder architecture, and you can see that the student used a sequence of linear layers followed by a batch normalization and a ReLU layer, or ReLU activation, and repeated this 3 times. And you can also see that the number of features basically compressed down gradually over the number of blocks. So from the input size image of the image, we are slightly going down block by block to the final latent dimension. And the decoder basically reversed this. So again, we have a sequence of blocks with linear layers, batch normalization, and ReLU layers, and then basically reversing the order of the feature dimensions until, again, we have the final number of neurons or the output size. And with that, in total, we have roughly 800,000 parameters of the model. And for the classifier, this was a bit smaller. So here, the student used also linear layers, batch normalization, but leaky ReLU in this time, and also dropout. And in terms of hidden dimensions, it was a bigger jump from the latent dimension to some hidden dimension until the number of classes in the last layer. And the classifier is basically the encoder together with this classifier, and this has roughly 600,000 parameters. So a quite structured architecture of all the components. And in terms of hyperparameters and transformations, we can see student also used a number of transformations, some random rotation, Gaussian blur, and also some slide translation, which are randomly applied. And also in terms of hyperparameters, there was nothing too crazy, but seems to be some good set, but nothing too crazy. And here we can see some reconstructions of the trained autoencoder from the student. So here you can see it's pretty accurate and pretty good reconstructions, going down to actually 32 latent dimension and uncompressing or basically decoding. So I think that's a pretty nice submission together with some training and trying out different architectures, I guess. Now I quickly want to compare fully connected and convolutional layers again. So for fully connected network, or MLP for multi-layer perceptron, this receives an input vector and transforms it through a series of hidden layers. And these hidden layers, depending on the definition, are the weights and also the activation functions or the nonlinearities. And with that, you get like some architecture like this, where I can see that the individual neurons in the layers are all connected to the previous neurons in the previous layers. So basically a dense connection through everything. So we are doing a lot of computer vision, and in computer vision, you oftentimes have images as input. So here you can see a very small image with 5 by 5 pixels, and we have 3 color channels for RGB. If we would also have 3 neurons, we would already have 3 times 75 weights. So basically, we would flatten this image into a vector of 75 elements, and then we would process it with 3 neurons. However, if we would have like a regular sized image of 1000 by 1000, then this would quickly explode to, for example, 3 billion weights if we would also have like a reasonable size layer of 1000 neurons. And this becomes impractical. And another disadvantage is why we could not use like a small image is that in this small image we would not contain useful information. So if you would compress or resize any normal image to 5 by 5, you could not really detect any patterns or try to classify it because there's not enough information. So somehow we need to find a better way to either be more efficient in terms of number of weights, or also be able to process bigger images. From the lecture, you already know that now we also know about convolutional layers. So again, we have the assumption that we have an image as an input, but now instead of having like this dense connection with the neurons, we use a filter or like a window and slide this over the entire image. And this is called convolution. And down here you can see an illustration. So again, we have an input image with 32 by 32 and 3 color channels. And now we also have a filter or kernel. In this case, it's 5 by 5 and 3 input layers or features. And this one is passed or slided over the entire image or being convolved. And in this case, we get one single output feature map, which also has a spatial dimension. And in this case, because we don't consider any padding, we don't get the same resolution as the input, but we're losing some pixels on the side. So we are only ending up with 28 by 28. The advantage of convolutional neural networks is that we basically learn translational invariant concepts. So basically, if you have a small window or small filter, and for example, if you're trying to detect edges, these should, like vertical edges, the concept of vertical edges should be similar no matter where in the image they appear. So basically, learning these translational invariant concepts is pretty efficient, and also that we are sharing the weights of these kernels. And obviously, we not only can try to learn a single feature, for example, like one direction of edges, but we can also try to learn multiple, like 5 or more features. So here, during training, we usually try to learn these filters from the data, but you can also hard code them, and then you don't need any deep learning, for example. So if you use any image editing software, you maybe know like some edge detection filters you can apply there. And something similar like this, we can simply apply with a hard-coded filter. So here we have a nice image of our building. And now we can define some very small and efficient kernels, like 3 by 3. And you can see that we weight the region of 9 pixels, like 3 by 3 pixels, with these values. So we're going to look at 1 pixel, and we weight basically all surrounding pixels with this kernel. And this is what we're going to repeat over the entire image for all pixels individually. And now we have 2 filters, and if we apply them over the image, we get two outputs, basically two activation maps, or two, basically results of this kernel. So in the left side, we can see it's trying to detect horizontal lines or edges, because it weighs basically the difference between the top and the bottom pixels. And on the right-hand side, we have vertical edges, because we're trying to, or we're basically weighting the pixels from left to right. So without any learning, we can already apply convolutions, in a sense, over images. And these filters, that's something that the network tries to learn. And usually these are not really interpretable, like just some concepts, nothing clear like edges. But it maybe helps to understand that, these try to learn concepts which start from low-level features, like maybe something like edges or blobs. And later on in the network, we're trying to learn higher level features over the combination of these hidden dimensions and hidden features. In the previous exercise, you already learned and tried to implement batch norm and dropout for fully connected layers. Now, for convolutional layers, the idea stays the same, but how they're being applied changes slightly. So let's have a look. So again, the two comparisons of fully connected and convolution. So for fully connected, we have like this dense connections. And for convolutional layers or outputs, we basically have a spatial output. So we have the number of activation maps or feature, and also the spatial size. And because now we have not only a vector, but like these spatial outputs, also the way how batch norm and dropout is applied changes slightly. So here the recap for batch normalization for a fully connected layer. Here we have a batch size n and the feature dimension d. And during training, we try to learn the mean and the variance over the feature dimension. So that's what you have been implemented last exercise. We are trying to learn across the feature dimension. Now for spatial batch normalization or convolutional batch normalization, the input is slightly different. So we have, as I said, this spatial input. And now we are trying to learn the mean and the variance across the channels. And because this is spatial, it would look something like this. So across all batches in our mini batch or samples in our mini batch, only across a single channel, we are learning this mean and variance. So that's something to keep in mind. It's like only a slight change in the implementation, going from batch normalization to something like batch normalization 2D. But that's basically the effect, that we are not only like flattening the features, but only applying them on each individual channel. And here's the comparison. For fully connected, we are only applying it across the feature dimensions. And in the convolutional or spatial batch normalization, we are applying it over each channel. Just to note, it's probably been mentioned in the lecture, or you already know, but there are also other normalization layers like batch normalization, which normalizes over the batch, but for the feature channel individually. Layer norm, across the layer. Instance and group norm, there are slight variations. There has been some papers about them that they improve the performance even further. if you're interested, you can look them up and try them out. Similar as for the batch normalization, for dropout, it also changes slightly if you now go to convolutional layers. So for the regular dropout, we just like set individual neurons or outputs to 0. If you would do the same thing for convolutional layers, it has been shown that this does not really improve the performance. Like if you could think that if we now have an image and corresponding or close pixels usually contain a similar information because they're like blurry, or at least there is some gradient, color gradient. So there is not really a reason why to drop out individual neurons, because like usually they should share similar concepts in a small region. Instead, spatial dropout would randomly drop out in entire channels, basically dropping out different concepts. And here is the comparison for this if you do it in PyTorch. So if you would use the dropout function or class on a flattened input vector, you can see it just sets the outputs to 0, like individually. If you would use dropout 2D with a like spatial input, like an image, then you can see entire feature maps have been set to 0. So here you can see the big difference that we basically want to drop out entire feature maps and not individual, like random individual neurons. There's also an optional notebook again as part of the exercise where you can try to implement this spatial batch normalization for yourself and try to understand the concept by basically implementing it yourself. All right, let's continue with exercise number 9, and this is going to be about facial key point detection. So let's introduce the task. So you're given some kind of image, and now we are going to use a convolutional neural network to get something like this. It looks a bit abstract, but these are basically landmarks or facial key points, and they have a certain type of notion. For example, we are looking for a key point at the nose, at the lips, for the mouth, or also for the left and the right eye. So as an image, as an input, we get a grayscale image. And in our case, we want to predict or regress 15 key points, and each key point has a 2D coordinate, like X and Y in the image. And here for this, you're given a data set of 1,500 train images and some for validation. And this time, similar to a previous exercise, it's not about accuracy, or basically we are not classifying the image into like some class, but we're trying to regress the individual points. And because of that, we are not computing an accuracy, but more like a score or like an error term. So that's how your model later is going to be evaluated. So we have our L2 or MSE loss, and we are basically predicting or calculating the score or the error over your entire data set. So we're just basically computing the distance between all the key points for every sample and just summing them, and taking the inverse is basically then the score. So you should not be surprised that in this case, you already need a score larger than 100 to pass the submission, but shouldn't be too complicated. So it's not like accuracy. It doesn't need to be 100% accurate, but just having a score above 100, which is basically just the distance between key points. With that, good luck with the exercise and see you next week.